This video will cover section 2.3, polynomial functions and their graphs. To begin, we have a graph here, and it's not a graph like the ones we're used to. It is a bar graph. So if we were to connect it, and I'm connecting the left side of every bar. Well, it should be a little rounder. You can see that it's going to take the shape of a polynomial, and for this polynomial we actually have an equation for it here, and it is a polynomial of third degree because that is the highest exponent. Also, we have the leading coefficient equal to -49, so that is why the polynomial has that end behavior. But we're going to discuss that in class. And before you ask, yes, this is a real graph, and it represents the 8 cases diagnosed in the United States from 1983 to 2008. The source is from the Department of Health and Human Services, and the data that they have, it goes from years 1983 to year 2008. You guys could see that the graph, it is increasing, and then after year 1993, it starts decreasing. Maybe there's a little slight increase here, and then it decreases again. So that is an example of a polynomial. And so what we're going to do now is we're going to go over the definition, formal definition of a polynomial. And trust me, when I go over these definitions, I want you guys to pay attention. If I underline something, please do underline it, highlight it, and don't just take them for granted, because you're going to take some classes that you might be required to read the textbook on your own. And so with that said, it is very important that you understand this type of writing, okay? I don't do it just to waste time. It's actually useful. So we have the definition of a polynomial function. We're going to let n be a non-negative integer. So what do we understand by non-negative? What does that word mean? It could be positive, and what else? 0. Or 0. Okay. So what we're saying here is that n is actually going to represent the degree of the polynomial, and you could see that here. So n represents the degree of the polynomial. So now what do we know about integers? Is 1/2 an integer? No. So they're like whole numbers, right? But yeah, I guess we could have said that, sure. We also include 0. Now, how about -5? Will that be a non-negative integer? No, because that's negative, right? How about 0.25? No. No, because that's not an integer. So the degree of polynomials, they have to be integers, and they have to be positive, or they could also be 0. So is that clear? Yes, the degree of a polynomial. All right, now let's go over the coefficients. And now for coefficients, we are using the letter A to denote that it could be a real number. And we're going to start from the coefficient of the term with the highest degree. That will be called A sub n. And A sub n is also the leading coefficient. So do you guys remember when you were in elementary school or kindergarten, and then sometimes you got to be the leader of the line, the lunch line, or PE?
I never got to be the leader.
No? Oh. Okay, we'll do something and you'll be the leader. But yeah, so imagine something like that, okay? So these are all the coefficients going to kindergarten, well, maybe college now. And then A sub n is the leading coefficient. So it's the coefficient of the term, like the one you see here, with the highest exponent. And the highest exponent will be n, and n will be determining the degree of the polynomial. Now here the subscripts, A sub n a sub n minus 1, and then we have that dot, 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 and then we have a sub 2, a sub 1, a sub 0. So what does this imply? The three dots. Mm-hmm. There are numbers in between, and also that they follow a pattern, right? So if you notice, the difference from the first, the leading coefficient, and the second one is just a minus 1, right? For the n, the subscript. So yes, that's what it is. And so let's look at the difference between the degree and the coefficients. Coefficients could be any real number. So does that mean could coefficients be negative? Yes, real numbers, they could be positive and negative. How about could coefficients be the square root of 2? Yes, that's a real number. Could a coefficient be 0.33333? Yes, that is a real number. So for coefficients, we have a wider variety, right? More options. But for the degree, they must be non-negative integers. Okay, so now let me explain to you why we have that restriction of, first, let's look at two examples of polynomials. And you can see here the degree is the highest exponent, so that will be 5, right? So the degree is 5. Now, what is the leading coefficient there? And we're going to call it a sub n. So that will be the coefficient of the x with the highest exponent. What will that be? Negative 3. Very good. Okay, now let's look at the second one. And what will be the degree of this polynomial? It's not 4. So think about what would you get if you multiply x times x? X squared. And then aren't you multiplying that times 3, negative 3x to the 4th? So if you multiply an x squared from here times x to the 4th, what are you going to get? X to the 6th. So what we're going to say is that the degree, which is n, is 6. All right? So if you are given a polynomial in factor form, then you still need to consider what would you get after multiplying all of the factors. Now, what will be the leading coefficient? And we'll call that a sub n. It's just negative 3. And that is because the coefficient of x is a 1, and coefficient of x is also a 1. So even after you multiply negative 3x to the power 4 times x, you will end up, your leading term will be negative 3x to the power 6. Okay? Now, let me show you why you cannot have exponents that are fractions, for example. So if I have a function, such as this one, when you have exponents as fractions, how could you turn that fraction into some other expression? It looks like a little house. A radical. So that will actually be the square root of x. Remember, the denominator of that exponent becomes the index of your root, and that is a 2. When we talk about square root, we don't really need to write down the 2, right? We know it is implied that it is the square root. We don't say the first root, we say the square root. So the square root of x plus 4. And we know that this example is a radical function. Okay, now let's talk about negative exponents. So if we have a function such as this one, What is that rule that we have, that when we have a negative exponent, and how can we turn it positive? So they're reciprocal, or you flip it, or you move it to the bottom, right? You'll have your own ways to say it. So 1 over x, and then this minus 7 here is just a vertical shift 7 units down. So how do we call this type of functions when the x is part of the denominator? Rational. So this is actually a rational function. See, so there are two reasons why your exponents cannot be fractions and they cannot be negative. Because if they were, then you will be talking about something that is not a polynomial in the case of a radical or a rational function. Now, remember the word that we were talking about, non-negative? Yes? So that includes 0, right? So does that tell me that a function like this will be a polynomial? What is x to the power 0? 1. It's a 1, right? So what kind of function will this be? Horizontal. It is a horizontal line, but it has a name. It's not increasing or decreasing. It is constant. It's a constant function. So I guess we're going to include those, and we'll also include parabolas, of course, quadratic functions, right? The exponents of 2. Linear functions, what is the degree of a linear function? A 1, right? So those, based on the definition that they're giving us, where n could be a non-negative integer, then I guess that will also include those constant functions and linear functions. All right, so let's look at the examples that we have on that same slide. And here, of course, we have the square root of x, right? So that represents x to the 1/2. That means it's not a polynomial. And here we have x squared on the denominator, so that will be something like the coefficient is -3, and then you will have x to the power -2. So that right there tells you that cannot be a polynomial, right? Okay, so let's go to the next slide. Do you guys have a question for me before I move on? So let's go to the next slide, and we're going to write down some definitions. First, polynomial functions of degree 2 or higher. So now we're leaving those linear functions and those constant functions out. Okay, we're going to go from degree 2 and higher. They have graphs that are smooth and continuous. Okay, so let's see what we mean by each word. By smooth, we mean that the graphs contain only rounded curves. With no sharp corners. And by continuous, we mean that the graphs have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. So I'll give you a few minutes to catch up. Now, once you take calculus, the definition of continuity is going to be completely different. Okay, you're going to have to check for other things. Now, right now we're talking about something easy. So by smooth, and let's look at the examples here. We have the example of two polynomials. And so you can see here that they are smooth. They have round corners. Here again, we have those round corners. And also they are continuous because I could trace them without lifting, in my case, my smartboard marker from the smartboard, right? In your case, pencil from the paper. Not a pen, pencil. Now here we have examples of graphs that are not polynomials. And so right here we have discontinuity. You guys see here there's a gap, right? So that gap makes it discontinuous. And then here we have some sharp corners, so they're not rounded. And that's why I'm going to ask you that when you graph a polynomial, you're very careful to not do that, and that you always have those rounded corners. Okay. So let's write down another definition here. So the behavior of a graph of a function to the far left or the far right, it's called end behavior. Okay, and now I want you to forget a little bit about increasing and decreasing, because when we used to do that, for increasing and decreasing, let's just write it down. We look at the graph from left to right. And when we talk about end behavior, we're going to look at the left side and the right side separately, okay? So we could have something that looks like that, and of course I'm missing some, and you'll see right now in the examples. Let's do that. And so for that one, instead of saying it is increasing and then decreasing and then, increasing, decreasing, increasing, decreasing, instead of looking at that, we're going to just see what's happening on the left side and the right side, okay? So we will say things like, it falls from the left, it falls from the right, all right? The opposite will be something like, let's do one that has one of each. So in this case, it rises from the left, it falls from the right. Okay, but let's do some examples now. So you guys see how it is different than increasing and decreasing. Yes? So let's talk about the leading coefficient test, and that's when we're going to use the leading coefficient test to determine the end behavior of a polynomial function. And we did a little bit of this in Algebra 2, so let's see. You guys might remember a little bit. So leading coefficient test, of course, the name, remember the leader of the line, right? That tells us that we're going to be, all the attention here is going to be to a sub n. So the leading coefficient test, we need to look at a sub n, right? And so we need to determine, is it positive or negative? That is basically what the leading coefficient test is. Now, also, we're going to look at the degree of the polynomial. So, look at n, and of course determine, is it odd or even? And I don't want you guys to get mixed up with, please don't write this down. Remember, when you guys were, or if you want to, you can write it. Actually, yes, write it, because some of you still don't know it. When we were looking at things like, I need some room. So write it on the side of your paper, okay? So for functions, not just polynomials, we have, we'll start with even. I like even first. An even function, that happens when f of negative x is the same as f of x. We also have odd functions. Well, before we get to that one, we had a little shortcut for that, and we used to look at all the degrees of every single term. But also, what this means is that those graphs, I'm going to give you the example of a parabola. If this is 2 and this is negative 2, we know that f of negative 2 is the same as f of 2, right? Because for those, they have the same y value, which is 4. That is an even function. And they are symmetric with respect to the y-axis. Now, for odd functions, we had to, again, find f of negative x. And so a function is odd when after substituting x with negative x, you get the opposite of the original function. This is what I mean by the opposite. So, in other words, all the signs changed. I'll give you an example. And this is x to the third power, which happens to be a polynomial. And if we take, let's say, 2 and negative 2 for the x, we get that 2 to the third power is 8, and negative 2 to the third power is negative 8. So we have something like f of negative 2 is equal not to f of 2, but to the opposite of that one. And when I mean the opposite, remember, I'm talking about f of 2 is 8, so since we say the opposite, it would be negative 8. And then what was the third one? If it's not even or odd, it is what? Either, right? So for those, after substituting f of x, we found that it was not equal to the original, and we also found out that it was not equal to the opposite of the original. So with those, oh, well, before we move on, this odd functions are symmetric with respect to what? The origin. Do not say x-axis, because anything that is symmetric with respect to the x-axis is not a function to begin with. So the reason I'm going over this, well, first is because some of you still don't get it. And also because we're going to keep seeing it. And it is actually important. You might not believe how important it is, but you will get a taste of that in dual credit pre-calc 2, but also in calculus. So when we talk about even functions, odd functions, that is something totally different from odd polynomials and even polynomials. All right? So odd polynomials are going to be polynomials where the degree is odd, just like that. So polynomials of degree 3, 5, 7, and so on. For even polynomials, we're just going to look at the degree, and if the degree is even, then that will make it an even polynomial. What I did on the previous slide, or what you wrote on the side of your paper, that was to test for odd functions and even functions. Okay, this is just to odd polynomials, even polynomials. They're two separate things. Yes? Okay. Now, the good news is that this test is a lot easier than the other. All you have to do is look at the degree of the polynomial and the leading coefficient, like I was telling you earlier. So we're going to look at the leading coefficient and the degree of the polynomial, and that's it. So let's go over this table quickly. Okay, and so we have, if the polynomial, well, let's do even. Even is always easier. You'll see why. So if your polynomial is even, you look at your leading coefficient, and if that leading coefficient is greater than 0, then you're going to, well, first of all, even polynomials have the same behavior left and right. If your leading coefficient is positive, it will be just like a quadratic function with a positive leading coefficient. It's going to be opening upward, right? So what we're going to say is that it rises to the left and it rises to the right. And also when we have, well, not also, but now if we have an even polynomial and we have a leading coefficient that is negative, that means less than 0. So then we're going to have this type of behavior. Just like a quadratic function, remember I told you a happy person smiles, or positive person is always smiling, negative people are usually frowning. So same thing. Yes? Am I what? Mm-hmm. Go to the CISD.
Yeah, I was there. I was doing the homework and then just wasn't loading. I was trying to fix it.
Or get another computer. Okay, so in this case we say it falls to the left and it also falls to the right. Okay? So for even polynomials, remember the quadratic function? Happy parabolas, sad parabolas, yeah? I think that one's pretty easy. Now let's talk about, and let's just write this down here. If a is greater than 0, that means that leading coefficient is positive, right? And if a is less than 0, that means that leading coefficient is negative. Okay, now let's go to polynomials of odd degree. Here we have the example. I can tell you right now that this is a polynomial of third degree, and you will learn why I know that in a minute. So when we have odd polynomials, if the leading coefficient is positive, then it's going to have this type of behavior. And so we refer to it as it falls to the left and it rises to the right. And keep in mind that when we say a sub n is greater than 0, we're saying that the leading coefficient is positive. All right, let's look at the next one. The leading coefficient is negative, less than 0. And so in this case, it will be the opposite end behavior, and we will refer to it as it rises to the left and it falls to the right. So a sub n less than 0, that means that the leading coefficient is negative. Now I'm going to give you a little trick to remember. And so that trick is that if the leading coefficient is positive, it will be mostly increasing. Do you guys remember linear functions, right? Yeah? So think about a linear function with a positive slope. Is that increasing or decreasing? Increasing, right? It should be leading to the right. Like that. Now, an odd polynomial that has a negative leading coefficient, and let's use again the example of a linear function, negative 2x. When the slope is negative, will that be leaning to the left or to the right? To the left. So we could say that it will be, well, for this one it is strictly decreasing, but for polynomials we will say it is mostly decreasing. I remember when I learned this for the first time, I used to have a little hard time remembering which was which. So that's a good way to remember. Yes, please. Is it an emergency? No. You can wait? Okay. What time is it? We'll take a break like in 10 minutes. Yeah? Could you wait 10 minutes? Okay. All right. So is that the end of that slide? Yes? Okay. So now let's see how we're going to apply this. Okay, so use the leading coefficient test, and that is the exact same way as I will ask you on a test, to determine the end behavior of the graph. Hold on. So for example 1, we're going to look at a sub n. Remember, a sub n is the leading coefficient. What is the leading coefficient here? A 1, right? It is the coefficient of the variable with the highest exponent. So that means that a sub n is positive, right? It is greater than 0. And now let's look at the degree of the polynomial. Actually, we should probably look at the degree first. The degree is represented by n is 3. And so is that an odd or even number? Odd number. So we're going to say that this is an odd polynomial. Not necessarily an odd function. It could be, I don't know, I don't feel like doing the math right now. But it is an odd polynomial, we know that for sure. So we know that the end behaviors are going to be different, right? Left and right. So we look at the leading coefficient, it is positive. So think about that linear function with a positive slope. So that will be something like that, right? So we could use that to determine the end behavior. So we're going to say that it falls to the left, and from the left, I forgot how to write it, and it falls to the left, okay. And it rises to the right. All right, now next one, example 2. Is the degree of that polynomial 3? It's not 3. What is it going to be? Think about it. 6. So if we expand this binomial, it will give us an x squared, right? And then here we have an x to the first power, And then here we have an x to the third power. So if we multiply all those terms, we will end up with x to what power? 6, right? 3 plus 2 is 5, plus 1 is 6. So we're going to say the degree of this one is 6. And so, of course, we all know this is an even number, right? So we're going to say that we're talking about an even polynomial. And so for those, they have the same behavior left and right, either down or up, or rises from left and right, or falling left and right. So let's look at the leading coefficient now. And the leading coefficient is just going to be that number, -4. So we say a sub n is equal to -4. That means that a sub n is negative, less than 0. And so because of that, it's just like the case of the parabola, right? So we're going to say it falls to the left, and it also falls to the right. Now, when you are graphing, it might be kind of useful if we use arrows. And I don't know if you noticed on the previous table. So for this one, to imply it falls to the left and it falls to the right, we could say something like this. The one that we did previously, we're saying it falls to the left and it rises to the right. Something like that. That would be useful when we're graphing.
Okay.
Example 3, we're going to do the same thing, use the and behavior. And if you notice, I don't know if you noticed, but this is actually the same graph, the same equation or function from the first slide. So let's talk about the degree. And the degree is 3, right? So n is 3, so we're going to say that it is an odd polynomial. So because of that, we're going to have distinct and behaviors. And the leading coefficient in this case, a sub n, is equal to -49. And of course, we know that's a negative number. And so because of that, think about that linear function with a negative slope. Is it like that or like that? Second one, right? So we're going to say, we could draw our arrows if you want to, and then you could write it in words. So we will say that it is, it rises to the left. And what else, Rebecca? And it falls to the right. All right. What else do we need to say? Use and behavior to explain why it is. Okay, so let's explain why it is only appropriate to model. It's only an appropriate model for AIDS diagnosis for a limited time of period. What do you guys think? Well, it's on. You could write. You could read it. Well, go ahead, Bessie.
I was going to say that graph,
The one on the right.
because it's flying to the left and then flying to the right.
Well, let's look at. They're talking about this graph here, and
I think I know why.
okay, tell me.
Well, this is only a graph from 1983 to 2008, so the amount of people who have gotten AIDS in the U.S. who actually go to get diagnosed may have changed the numbers. So this graph is only appropriate for this time frame.
Okay, so this function and its graph is only appropriate for a limited time frame. Okay, that sounds good to me. Yeah. All right. So let's go to the next, the last problem before we go on break. Okay, so we have those graphs, and then it's actually the same graph. But here what they're doing is changing the a different view. Like, you know, when you go to zoom, and then you could set your settings. So for the first one, they have the x-axis going from -8 to +8. And they have the y-axis going from -10 to +10. And so this number here, it tells us the units, so they're going by ones, okay? Now for the second graph, and we're talking about the same function, all right? For the second graph here, the x-axis is going from -10 to +10. That's why we have -10 and 10. And the units are going by ones. However, now the y-axis, or the vertical axis, is going from -1,000 to +750. And a good way to achieve this on the calculators is by going to, well, for your calculator, it will be menu, and then I believe it's something that says graph zoom.
Yeah. Window zoom.
Window zoom, okay. Window zoom, and then also you will go to the function that says zoom fit, and I believe that's letter A for your calculator. So that's how they achieve that one. Sometimes you might be required to do that. So you see, if you were to just graph it with this first window, it might look like you're talking about a polynomial of odd degree, right? But then if you zoom, and if you zoom in, that's what I'm thinking they did, you could see clearly that we're talking about a function, not a function, a polynomial. Well, it's still a function, a polynomial of even degree, right? So therefore, it does have the same n behavior. We have the leading coefficient is, so a sub n, it is -1. The degree is 4. So we have a negative leading coefficient, and we have an even degree. Okay, so just so you know, sometimes it might be necessary to change the window. So I'm going to pause the video, and then let's go on. So now we're going to talk about zeros of polynomial functions, and as you may know, we have several words for that, right? We can call them roots and other things. But let's write down some statements. So if f is a polynomial function, then the values of x for which f of x is equal to 0 are called zeros of f. So here I'm referring as the values of x, right? Those are the ones that are called zeros. Also, the values of x are the roots or solutions of the polynomial equation f of x is equal to 0. So again, roots and solutions. And those are the solutions to the equation f of x is equal to 0. So here what we're saying is that the y value is equal to 0, right? Now, how can we translate that into x-intercepts? So we're going to say that each real root, so we're talking about roots that do not have imaginary numbers. Each real root appears as an x-intercept of the graph of the polynomial. So we discussed this a little bit when I was talking about when we were teaching, when we were learning section 2.1, complex numbers, right? Okay, now let's see how we're going to find the zeros. And so for that, we're going to rely on factoring sometimes. Other times, we're going to use the quadratic formula. And then the next section, which is 2.4, we're going to use other methods such as long division, synthetic division. You guys remember that? Synthetic division? Everyone loves that. And also other rules and theorems. So for this one here, we can factor it pretty easy. Do you guys have an idea how to factor it?
I factor out an x.
Well, this one doesn't have an x. How about by grouping? So x cubed by 3x squared. And now, instead of writing minus and then my next group, what I'm going to do is the following. Well, let me tell you why I can't do that. If I write it that way, then I'm saying that I have negative x, but I'm also saying that I have positive 3. And that's not what my function has, right? We have negative x and negative 3. So it's just a lot easier if you have a positive sign in between. You must have a sign because you don't want to say that the two binomials are multiplying each other. All right, that's not the purpose of factoring by grouping. So we'll have plus, parentheses, negative x, and then the minus 3. Now from here, we could factor the greatest common factor. So x squared, very good. And if we factor x squared from here, Jesus, what would I get? We factor x squared from here. So remember, you're kind of like dividing x. And then if I factor x squared from here, all it 3. Positive or negative? Positive. So positive 3. Now the next one, there's nothing we could factor, right? Negative 1. So we factor a negative 1. And if we factor a negative 1 from here, what will we get, Jennifer? From negative x plus 3. Very good. Yes.
We don't put the plus anymore? Is that like
well, no, we don't need it anymore. Now, our factor, it is, the first factor is going to be the one that they have in common, right? Which is x plus 3. It just happens to be a binomial. So that will be our first factor, x plus 3. And then our second factor, oh, and this should, I don't know why I have a negative here. That was just an equal. So if you have a negative there, please correct it. Also, we're trying to find the roots, right? So we want to find those solutions that will make f of x or y equal to 0. So I'm going to equal that to 0. So again, our first factor is the one that they have in common, x plus 3. And our second factor comes from here, x squared minus 1. Okay, and now can we factor any further? Okay, so Brandon, that is the difference of squares, right? Because x squared is a perfect square and 1 is also a perfect square. You remember how to factor those?
Would it be x plus 1 plus minus 1?
Very good. So difference of squares, very easy to factor. Take the square root of the first term, square root of the second term. You have one positive, one negative in between the two terms. Nice. Now that we have all factors there, yes?
Where did x squared minus 1 come from?
Oh, from here.
Oh.
So when we factor by grouping, first we make two groups, and then we take the GCF of the first group, so it will be this one. And then the GCF of the second group, that will be the negative 1. And then the next step, we take the factor in common, which is the x plus 3, and then the other one is what is left, the GCFs. Okay, so now from here, what we need to do to find the zeros is we're going to create three linear equations. So the first one will be 0 is equal to x plus 3. And then we have 0 is equal to x plus 1. And then we have 0 is equal to x minus 1. So here we will solve for x. So x is equal to negative 3. X is equal to negative 1. And x is equal to positive 1. And you guys are going to get very good at this, I promise. All right, so now it is not part of the question, but I just want to do a rough sketch of the graph. Now, so we know that the zeros or roots or solutions, are they real numbers? Yes. They are, right? So they are actually going to be x-intercepts. And what is the degree of this polynomial? 3, right? So that means we are talking about an odd polynomial. What is the leading coefficient? 1. So that means it's positive, right? So is it going to be like that? First one, right? See, and it is a degree 3, so that means that it could have at most 2 turning points. So I'm just going to do a very rough sketch. It's not perfect. Well, however, could we find the y-intercept quickly? I think so. Remember, if it's a y-intercept, that means that the x-coordinate is 0. So pretend you put a 0 for every x here. What are you left with? Negative 3. So the y-intercept is at 0, negative 3 here. So I'm just going to do a rough sketch here. See? Pretty cool. Well, I think it is. Yeah.
You have negative 3.
Uh-huh.
Would the y value for like the first curve be 3?
Not necessarily, because it could be something else, because we're not really saying that it is symmetric with respect to this point. If it was, yeah, but sometimes it could be. All right, so let's go. I hear a lot of talking, guys. Come on, next problem. Okay, so find the zeros of this one. Yeah. I'm sorry? There was a problem below?
No, I think let's leave it 11:45. You said something about being in.
Oh, okay, I have 3 minutes. We can find it. We can finish this. But thanks for reminding me. It's so nice of you. Well, I still need to wait for Mr. Akita. Okay, so find all the zeros of that, and we're also going to find them by factoring. so let's see. What I'm going to factor this negative is kind of bothering me, so I'm going to factor out a negative x squared. So if I do that, we'll get positive x squared plus 4x minus 4.
Actually, I think the 4x would be negative and the 4 would be positive. If you're factoring in extra.
Okay, yes. Thank you.
Why not?
Why? Okay, so negative 4x plus 4. All right. So be careful with that. I was just trying to show you what not to do. We rehearsed that at home. No, we didn't. Okay, now we have a trinomial square, right? So we can factor that one. It will be x. The sign is positive, so that means both signs of the binomial, the ones in between, are going to be the same. However, we have a negative here, so that means both are negative. Factors of 4, we could use 1 and 4 or 2 and 2. Right? I'm going to go with 2 and 2. And remember, we're finding the zeros, so we're making this f of x or y equal to 0. Now here actually we're done factoring, but what I want to do is just write it in this way. And so let's go ahead and, well, let's finish solving for it. So taking the problem from here, if we create 3 different equations, we'll have 0 is equal to negative x squared, we'll have x minus 2 is equal to 0, and x minus 2 is equal to 0. So here we will have x is equal to 2, x is equal to 2, and here we'll have, if we multiply by negative 1, we will get 0 times negative 1 is still 0, and then if we take the square root, we will also get 0. So those 3 are x-intercepts because they are real numbers. However, we have this one repeating, right? So we're going to say that it occurs twice. So because of that, we call it even multiplicity.
Teachers, please excuse the interruption. Web Society members, please remember we have our first lunch meeting today.
Okay, let's just finish there. So I'm going to pause and then we'll continue with this lesson on Wednesday.